Next, let us define linear and nonlinear materials. Before that, let us review the linear functions. In mathematics, we know that for linear function, they can satisfy the following relationship, which is f of a x1 plus b x2 can be written as a times f of x1 plus b times f of x2. Any function satisfy this kind of relationship, we call it linear function. So following the same properties, let us define the linear material. For linear materials, we know that the D field can be expressed in terms of E field. So we can say that D field can be function of E. So consider two external fields E1 and E2. The D field, D of function A1 E1 plus A2 E2. For a material, if this material is linear, so the D function can be written as A1 times D of E1 plus A2 times D of E2. This means that the effect of two fields is the summation of effect of each field. So any material satisfy this kind of relationship, we call it linear material. Besides, for B field, for linear material, the B field can also be written as B of A1 H1 plus A2 H2 can be rewritten as A1 B of H1 plus A2 times B of H2. These are the properties of linear materials. And now let's consider nonlinear material. For nonlinear materials, it means that the material properties is changed with the magnitude of the E field. This means that for larger E field, you have one properties, but for smaller E field, you will have different properties. This kind of material, we call it nonlinear materials. This also means that the epsilon r will vary with the absolute value of E field. Okay, so let me show you one example. If the polarization, electric polarization P can be expressed in this way. Epsilon 0 times chi 1 plus chi 2 absolute value E plus chi 3 absolute value of E, the square of the absolute value of E. If the material properties have the relationship like this, you will see that if you have larger E field, the P will become very large, And if you have smaller E field, the P will become very small, but they are not in the proportional way. That is, P is not just in proportional to E, they are in a nonlinear relationship. Okay? But in your research or in your consideration, if the absolute value of E is small, even this material is nonlinear, the nonlinearity is not obvious. However, for a nonlinear material, if the absolute value of E is large, the nonlinearity will be also obvious. In optics, we frequently use nonlinear materials to design some optical devices. If you want to learn more about the nonlinearity of a material, or if you want to learn nonlinear optics, you can go to the lecture provided by Professor Lin Yuanyao or Professor Li Zhaokui. In their lectures, you will learn a lot of nonlinearity in optics. Here I will show you one example formed by nonlinear material. This is the all-optical switch. We know the switch means that you can control the light, control the direction of light, or control the light to be on or off. Optical switch means that you can use the light power to control the power direction, or to control the path of the power. How to do it? Here we design a device like this. We call it Mach-Zehnder interferometer. For the MZI, we will learn it in chapter 2 or chapter 3, I forgot. Okay, this is a Mach-Zehnder interferometer, and light power is launched into this port, and this part is a 3 dB coupler, which will separate the light power into two paths. This 3 dB coupler will equally separate the power into two paths. And these two paths have different material. Here, we have nonlinear material. And these two power will go to another 3 dB coupler, and they will combine these two. So these two paths will have different phase velocity, or have different phase difference. So here, according to the phase difference, you can decide the total power will go this way or go the other way. Okay. So initially, if we design this device to have power inside this port and outside from this port, and for smaller light power, this region have no difference with others, so we can have power output from this port. But however, for larger light powers, the nonlinearity of this region will make a large contribution to the phase difference of these two paths. As a result, it may form destructive interference here and form constructive interference here. Then light power input this port and will go out from the other port here. So by using of this nonlinear material, we can control the phase difference of these two light paths to make the power go through one port or go through the other port. This depends on the input power of the light. Okay, so you can use the light power to control the output port of the input signal, and we call it as all optical switch.